The VOR provides navigational signals that enable a pilot with properly equipped aircraft to determine bearing relative to a VOR facility. The VOR transmits 360-degree radials, one for each degree of azimuth around the facility. A radial connecting two VORs is known as a Victor airway. VORs are primarily classified as en route navigation aids. Victor airways are depicted as black solid lines on an instrument flight rule en route low altitude chart, and as thick faded blue lines on VFR sectional charts. They are identified by the letter V and a number. For example, a pilot could say that she is flying Victor 8. The VOR has a designated standard service volume, or SSV. There are three distinct service volumes: T for terminal, L for low altitude, and H for high altitude. Coverage is not available in a cone of airspace directly above the facility up to 1,000 feet AGL, or above ground level. Take a moment to observe the illustrations shown to determine the different ranges and altitudes for each service volume. Moving on to the VOR characteristics. The VOR has a frequency range of 108 to 118 MHz with 50 kHz channel spacing. The VOR radiates in all directions, or omni-directional. The output power is a maximum of 200 watts, but is ultimately set by flight inspection or with the help of flight inspection to achieve a minimum coverage of 40 miles. The facility ID consists of Morse code keyed at 1020 Hz using 3 or 4 letters. The VOR is capable or can also be used by air traffic control to communicate with pilots if enabled. And lastly, the heading is insensitive, meaning the VOR information received by an aircraft is not influenced by the attitude or direction of flight of the aircraft. Let's now discuss the VOR radiated signals, beginning with the reference signal. The reference signal is a 9960 Hz subcarrier, frequency modulated by plus or minus 480 Hz at a 30 Hz rate. It is amplitude modulated onto the carrier at 30%. It is of a constant phase at any azimuth around the facility. Next is the variable signal, which is a 30 Hz double sideband suppressed carrier signal in which the sidebands, sideband 1 and sideband 2, are in quadrature from each other, or 90 degrees phase difference, resulting in a space modulation of 30% signal which bears direct relationship to the azimuth angle at the point of reception around the facility. Moving on to the rest of the VOR radiated signals, the identification, as previously discussed, is a 1020 Hz Morse code facility identification code that is amplitude modulated onto the carrier at 5% and keyed every 7.5 seconds. Lastly, we have voice, if enabled. This could be a voice identification instead of Morse code. That would be modulated at 30%. And lastly, we could have air traffic control voice modulated onto the VOR also at 30%. This would be typically NOTAM information or weather information that is automatically broadcast over the VOR, again, if enabled. Let's now look at the VOR frequency spectrum. The RF carrier is shown in black as the center frequency with the 30 Hz sidebands in brown providing the variable signal. The reference signal in blue is the 9960 Hz subcarrier with a slightly wider span due to the plus and minus 480 Hz deviation. And then the VOR keyed ident tone and any speech are also transmitted on the carrier, shown by the gray and purple bands. The Omni course can be defined by the number of degrees that the detected variable 30 Hz signal lags the detected reference 30 Hz signal. This definition is fundamental to understanding the VOR and will be referred to constantly in this lesson. All aircraft will receive the same audio reference signal regardless of their location. However, not all aircraft will receive the same audio variable. The number of degrees the variable 30 Hz audio lags the reference 30 Hz audio signal is the coarse radial. So to reiterate, aircraft receive both the reference and variable signals. The reference signal consists of the 9960 Hz plus or minus 480 Hz that's FM modulated and radiated out of all 4 antennas in phase. All aircraft around the station pick up the reference at the same time. Aircraft receivers will detect a 9960 plus and minus 480 Hz FM signal as a 30 Hz sine wave. The variable component consists of a phase difference of the sideband 1 and sideband 2 adding to or subtracting from the carrier radiated pattern, producing a rotating Limacon pattern, as we'll later see. Not all aircraft around the station receive the same RF signal strength. Aircraft's receiver detects a changing RF signal strength as also a 30 Hz sine wave. Let's now review a VOR block diagram, starting with the RF transmitter, which provides the modulated carrier to the antennas and unmodulated carrier to the goniometer. The goniometer generates the 2 sideband suppressed carrier signals, and coax bridges A and B route the RF inputs into the antenna array to provide impedance matching for maximum power transfer and are used to isolate the different inputs from one another and to provide the proper RF phasing to the antennas. As for the antennas, they consist of 4 alpha loop antennas in yellow, and they radiate the various RF inputs, creating this VOR radiation pattern. There are additional stubs that act as a capacitive section of coaxial line for maximum transfer of energy, or in other words, impedance matching. We also have balance, which are transformers that transform an unbalanced transmission system to a balanced antenna system, where again, for more impedance matching. And within the antenna is a crossover strap or crossover phasing strap, where the north antennas are strapped to the right and the south antennas are strapped to the left to provide the required phase shift before radiating. Let's now discuss the VOR signal flow, beginning with the RF transmitter. We can see at the top left the 9960 Hz plus and minus 480 Hz signal originating from the audio generator. It deviates at a deviation ratio of 16:1 and is routed to the RF transmitter, where it amplitude modulates the carrier. The unmodulated RF output is a low-level carrier output that is routed through a phaser to a block labeled the goniometer. The phaser is used to set the phase of the goniometer outputs, sideband number 1 and sideband number 2, to match the carrier phase. Let's now discuss the goniometer block, starting with the sideband number 1 output. This RF output is a double sideband suppressed carrier signal that's modulated at a 30 Hz rate. This output is also referred to as the positive sign output from the goniometer. Notice that the first lobe in the green sideband number 1 signal has a plus sign. This means that the RF energy is in phase with the carrier RF. The crossover point or null on the waveform is where the sign changes to negative. This indicates that the RF energy in this lobe is exactly 180 degrees out of phase with the carrier. Now moving on to sideband number 2 that is colored red. It is the exact same as the sideband number 1, however this is often referred to as the negative cosine, and this RF output is also in phase and out of phase with the carrier using the positive and negative denotions. Mathematically, the difference between the sine and the cosine functions is 90 degrees. When the sideband number 1 output is at a null or crossover point, the sideband number 2 goniometer output is at a maximum. And conversely, when the sideband 2 output is at a null or crossover point, the sideband number 1 output is at a maximum. In this animation, we can see how the carrier RF path flows from the RF transmitter through the bridges and out of the antennas, all in phase. Note the isolation occurring at the bottom of each bridge, bridge A and B. This is to isolate the RF carrier energy from the goniometer. Also note that Antennas are all in phase due to onboard antenna strapping. In this animation, we can see how the sideband RF paths flow from the goniometer through the bridges and out of the antennas oppositely phased. Note the isolation that occurs at the top of each bridge to isolate the sideband energy from entering into the carrier. Let's now discuss the goniometer's audio phasing in more detail. There's an angle associated with the position of the goniometer output waveforms. It's referred to as ρ and serves as a reference for describing each waveform. Its relation to the goniometer is such that ρ equals 0 degrees when sideband number 1 output is 0 and sideband number 2 output is at its maximum amplitude with respect to the carrier. The negative sign means the RF phase is exactly 180 degrees out of phase with the carrier, and the positive sign means it is in phase with the carrier. This means these signals will either add to or subtract from the carrier signal. The difference in the sine and negative cosine function is 90 degrees. Therefore, the two goniometer outputs are in quadrature. Let's now look at the resultant RF pattern when carrier and sidebands combine in space starting at ρ equals 0 degrees. Remember, the reference carrier is radiating from all antennas all of the time. Only sideband number 2 amplitude is present from the northeast and southwest antennas. The northeast subtracts from the carrier and the southwest adds to the carrier, giving the limacon pattern. Maximum limacon radiation is at azimuth of 225 degrees and a minimum limacon radiation at an azimuth of 45 degrees. At ρ equals 45 degrees, sideband number 1 and number 2 are radiating out of all antennas, and so is the carrier. The northwest and southwest antennas are in phase with the reference carrier, resulting in a maximum composite RF signal to the west. Since the southeast and northeast antennas, sideband 1 and 2 respectively, are oppositely phased from the reference carrier, it results in a minimum composite RF signal to the east, thus maintaining the limacon radiation pattern. At ρ equals 90 degrees, only sideband 1 amplitude is present from the northwest and southeast antennas. The southeast subtracts from the carrier and the northwest adds to the carrier, giving the limacon pattern shown. Maximum limacon radiation is at azimuth 315 and minimum limacon radiation is at azimuth 135. At ρ equals 135 degrees, sideband 1 and 2 are radiating out of all antennas again. The northwest and northeast antennas are in phase with the reference carrier, resulting in a maximum composite RF signal to the north. Since the southeast and southwest antennas are oppositely phased from the reference carrier, it results in a minimum composite RF signal to the south. At ρ equals 180 degrees, only sideband number 2 amplitude is present from the northeast and southwest antennas. The southwest subtracts from the carrier and the northeast adds to the carrier. Maximum limacon radiation is at azimuth 45 degrees and minimum limacon radiation is at azimuth 225 degrees. At ρ equals 225 degrees, sideband 1 and 2 are radiating out of all antennas again. The northeast and the southeast antennas are in phase with the reference carrier, resulting in a maximum composite RF signal to the east. Since the northwest and the southwest antennas are oppositely phased from the reference carrier, it results in a minimum composite RF signal to the west. And at ρ 270 degrees, only sideband 1 amplitude is present from the southeast and northwest antennas. So the northwest subtracts from the carrier and the southeast adds to the carrier. Maximum's at 135 and the minimum is at azimuth 315. And rounding out the radiation pattern, we see at ρ equals 315 degrees, the sideband 1 and 2 are radiating out of all antennas. The southeast and southwest antennas are in phase with the reference carrier, resulting in a maximum composite RF signal to the south. Since the northwest and the northeast antennas are oppositely phased from the reference carrier, it results in a minimum composite RF signal to the north. And we are now back to where we started. We made one complete rotation, which occurs every 33 milliseconds, or 30 revolutions per second. Remember, the reference 9960 plus and minus 480 Hz FM will detect in the aircraft as a 30 Hz sine wave. Also, the variable will be detected in the aircraft as a 30 Hz sine wave, but due to the changing RF signal strength of the rotating limacon pattern, brought about by the sidebands combining with the carrier, also known as space modulation. The depth of space modulation in the VOR is ideally 30%. Let's now review a simplified VOR aircraft receiver, beginning with the modulated RF carrier coming in from the aircraft antenna, hitting the 9960 Hz detector, stripping the RF carrier, leaving only the audio component, and then the FM detector removes the frequency modulation and distills it down to just the 30 Hz reference signal. Also, the 30 Hz AM detector detects the changing RF signal strength produced by the rotating Limason pattern and detects it also as a 30 Hz variable. They both enter into the phase comparator, which compares the phase of the variable input to the reference input. The required azimuth is set up by the OBS knob, and a DC voltage is sent out of the comparator to the indicator. The DC voltage is the deflection voltage for the needle on the course deviation indicator. If the aircraft is on course, the needle stays in the middle. If the aircraft is off course, the needle will deflect left or right. Each mark, left or right, is 2 degrees of error, and the pilots are taught to fly towards the needle to get back on course. Let us further discuss some key components of the VOR antenna system, beginning with the alpha loop antenna array. Note that 4 alpha loop antennas are mounted together to make up the array. The alpha loop antenna is constructed of 4 half-wave elements folded and arranged so that the elements' midsections form a square approximately a quarter wavelength per side. In an alpha loop, broadband operation is secured by making the width dimensions of the radiating faces relatively large. In addition to making it a more efficient radiator over a band of frequencies, the broadband characteristic also tends to make the loop more stable in operation. It is less subject to impedance changes as a result of weather conditions or moving objects in the immediate vicinity. Each radiating face, which is a midsection, has a current amplitude maximum at its center to approximately 70% of maximum at the ends of the midsection. If current maximums are correctly centered on all 4 alpha loops, the far field radiation will be equal in all directions, creating a circular pattern. The antenna currents can be adjusted by the use of end plates. In this example, we can see that these end plates are maladjusted and are too short. This condition would radiate a non-circular far-field radiation pattern. In this example, we can see that the current maximums have moved off the center towards the end plates because the end plates are set too long, and again, a non-circular radiation pattern will result. This is often referred to as octonal error. And here we can see the end plates are properly adjusted, producing a circular radiation pattern. Looking at these 2 images, we can see the schematic representation to the left of a coax bridge and the actual field installation of what that looks like. Note the carrier and sideband wattmeter bodies, stubs, and antenna feed line stretchers for final adjustments. Because the antennas in the VOR system are designed to have broadband characteristics, they will exhibit an impedance of 1200 ohms in the frequency band of 108 to 118 megahertz. A balun is installed under each antenna then to transform the unbalanced transmission system to a balanced one. There is also an impedance transformation that occurs to bring the antennas down to appear as 300 ohm loads. However, since an impedance mismatch is still present, VOR systems use stubbing to reduce the voltage standing wave ratio, or VSWR, on the transmission feed lines down to 50 ohms to match the transmitters. Here's a close-up of the crossover strap on the alpha loop antenna between the RF feed line input to either the left terminal A or B terminal right, where the balun is connected to. The north antennas are strapped to the right, and the south antennas are strapped to the left. The antennas strapped to the right are the north antennas and radiate the RF in phase with the received energy on the RF feed line input. The antennas strapped to the left, or the south antennas, will radiate the RF oppositely phased, or 180 degrees out of phase with the received energy on the RF feed line. And in summary, we'll use this illustration to wrap things up. We can see the positive sign sideband energy is used to represent what is in phase with the carrier. The negative sign is sideband energy is what is out of phase with the carrier, thus adding to or subtracting from the carrier to create the Limousin pattern.